Hi everybody, this is Dr. Bardot, and this is going to be a little tutorial about area of circles and also area of irregular shapes. So one of the things we saw in GeoGebra is that the circumference, which is basically the perimeter of a circle, is 2 pi times the radius. We're going to use that fact to calculate, or at least estimate, how you would calculate the area of a circle. So let's draw a circle. Something pretty close. And what I want you to imagine now is that you take the circle and you cut it at the center into pie shapes. And let's imagine doing that a lot. So the pie shapes are really, really, really thin. And then what we're going to do is arrange those pie shapes. So I'm going to take one of those pie shapes and put it that way, and then the next pie shape is going to be down here, and the next one's going to be up there, and the next one's going to be up there, and the next one's going to be up there, and the next one's going to be up there, and the next one's going to be up there, and so on and so on and so on. And I drew these pie shapes pretty thick, actually. So if I cut them really thin, then these lines that you see over here are almost vertical. And so what does this mean? This means that we get sort of a squiggly line on the top, a squiggly line on the bottom, and these vertical lines on the sides. So this is made up of lots of slices of the circle. And how tall is one of these slices? Well, each one of these was a radius, so it's radius tall, this rectangular thing. And how wide is it? Well, what's on the outside is all the pieces of the circle. And so that's the outside of the circle. So we have put the outside of the circle along here. And we put the outside of the circle along the bottom. So that's my cat. We've separated it into two pieces. So along this, since the whole outside of the circle was 2 pi r, this top piece is pi r, and this bottom piece is pi r. And so we have a rectangle whose dimensions are pi times the radius and is radius tall. So the area is pi r squared. I want to give you some tools on how to deal with shapes that aren't triangles or rectangles or trapezoids or things like that. So here's a hexagon. How can you find the area of this? Well, we're going to talk about lots of different ways. But one way, just to realize, is that, and this is one of the reasons we study triangles so much in geometry class, is that you can break up shapes into triangles almost always. So a triangle is a very powerful shape. If we can figure out how to find the area of the triangle in as many ways as we can, we'll be better off. So that's one way to do it. And another way to do it is to take your shape and put it inside of a more standard shape, say like a rectangle, and then find the area of your rectangle and take away the pieces that aren't there. So, so enclosing your shape in another shape might be, and that's a very good idea in a case like this where you've got something that's sort of a rectangle to begin with. So you find the area of this larger rectangle, then break that smaller region into two other rectangular regions and calculate their area and take that away. One other idea that's very powerful is the idea of parallel transport. So this is the idea that if you take a shape and cut it into lots of little parallel strips, very, very small parallel strips, you know, like this, then you could sort of rearrange those strips in any way you want. And one thing you could do is sort of slide them all against this red wall, and when you did that, you'd get something else, but it would still be exactly the same width on the bottom, because that bottom strip is still the same length. But you wouldn't have changed the area. So every triangle I draw that has this base and has a point on the top over here, maybe I'll pick a different color. So let me pick this point over here. If I go from here to there, this green triangle has the same area as this black triangle here, which has the same area as the red triangle. Okay, and you know, if I drew a yellow triangle with a vertex there, as long as it has the same base, it's going to have the same area. So all of those have the same area. This is very useful a lot of times because you can take a very complicated shape and sort of straighten it out into one that is much simpler to think about. So this is most useful, I think, in sort of 3D cases when you're looking at volume. So if I look at, say, the volume of a cone, when it's a nice straight cone like that, people understand very nicely that there's a relationship between the base and the height, and that helps you find the volume. But if I take a cone that's kind of crooked, sort of what to do? Well, what you want to do is just pretend that this cone has been sort of smushed so that it's all straight up and down again. You just need to find out how tall it is. Still, no difference. So let's quickly review what we saw here. The first thing is we saw that the area for a circle is equal to pi times the radius squared. We saw that by cutting it into little pi pieces and creating a rectangle, basically, that's r tall and pi r wide. We learned that you can cut shapes into triangles. Or you can put a box around them. And that can help you calculate the area. And then finally we learned about parallel transport, which says that if you sort of slide things parallel to each other, you don't change the area.